vectors. So a couple key definitions. The difference between a scalar and a vector is that when you just measure something by its length, its weight, just one measurement is called a scalar. So if I said, I went 5 kilometers, you don't know where I went 5 kilometers, it's not very clear, then that distance is a scalar. But if we add to that a direction, we get something called a vector. So if I told you I went 5 kilometers north, then you've got a length and you've got a direction. That makes it a vector. So we call displacement a vector. We call velocity. And so this is something that for a long time in science, you're like, oh, velocity is just another word for speed, right? What's your velocity? What's your speed? Now, technically, velocity should have a direction. I'm going 20 kilometers per hour east. I'm going in this direction, right? So sometimes it gets mixed up with speed because you say what your velocity is because you know well, I'm going this speed and I know I'm going in that direction, but technically, you need that direction for it to be velocity. So here's our first little challenge. We've got a list here. I want you to try them first on your own, then the ones that you're unsure of. Either put beside them the letter V for vector, S for scalar, and some of them could be neither. And we'll go over these in a little bit. So try them first on your own, then discuss them, which ones you're kind of unsure with, your neighbor, and we'll then go over all of them. All right, let's see how you did. Scalar, temperature doesn't have a direction there. Truck, no direction, scalar. Water flowing due north, okay, we've got a direction and a length. Wind blowing from the south, here you have a direction, but you don't know what its magnitude is, so it's not a vector here yet. Upwards vertical force, so we've got a measurement and a direction. Rock has a mass of 5 kilometers, nice. 5 kilograms, scalar, box is scalar. Car is speeding eastward, just a direction, so that's neither. Rock has a density of 5 grams. Vector, wind blowing from the south, vector. Stone dropped. This one is a vector because it's going straight down. And there we have the difference between a scalar and a vector. So notation-wise, how do we draw a vector? We draw a vector with a straight line with an arrowhead. Okay, and that arrowhead sometimes is in the middle, sometimes is on the end. I find lots of students like to put it on the end, but you'll see in some textbooks they have that arrowhead in the middle. It can be either way. Okay, I think I tend to draw it more on the end as well. So position vector OP has the coordinates x, y. So let's say this point was 2, 3. That looks more like 3, 3, but just so that we have different numbers. Because if you use the same numbers, it doesn't really help you understand which one goes where. Sometimes we write a vector as a column. So we have 2, 3, almost like a matrix. So there's a little bit of connection between matrices and vectors and how we write them. So we can write it as a column vector. Now, in the exercises that you will get, the textbook likes to denote a matrix. So this is the matrix A. They like to denote it with bold. Now, bold is not so easy to do while you're writing with a pen. I mean, I guess you could go over it a bunch of times or something. But generally what we do is we write a vector by over top drawing an arrow. And sometimes you will see the arrows like this, and sometimes, and I think this might just be laziness, but sometimes the arrow only has the top part to it. And I think that's so that you can draw it without lifting your pen and do it quicker and not have to worry about the extra little bar. I'm not sure. So I remember drawing always, maybe I was just lazy, always with one arrow. Maybe it should be a full arrow over top. The bold seems to take a long time to do. Doesn't seem to be very efficient to write something with by hand and making it bold. So you will see in the notes, I often have the bold. Okay, when we write things, we're often going to write it with an arrow over top. Sometimes we write it and we call a matrix A. I mean, not a matrix, we call a vector A. Then we just write a letter. But sometimes you write the vector based on its endpoint. So this goes from O to P, and so we can write OP with an arrow over top. That really makes a lot of sense for what's happening. Okay? So here we have the point 6, 3. That's a vector from O to A, and we can write that as a column vector, 6, 3. Right, and here's the idea that they can also write things as bold letters. Oh, sometimes they're underlined instead of with the arrow over top. Okay? So notation-wise, when you get similar math that was learned across various areas in the world, and different areas develop different notations, some of those notations have stayed, and so we get the same thing in different forms. They haven't decided, no, we are going to attack another country to destroy their vector notation and get rid of it forever. So we see these different things. So another one is underline. Okay, I'm going to say, for us, let's go with the arrow over top as our general way. But if you want to do any other form, right, as long as you're not making up something new. Oh, okay, no, I won't get creative now. So the magnitude or modulus or length of a vector is denoted by the absolute value bars. Because technically, that's what an absolute value bar is. When you do the absolute value of -3, you know from all your math that it's +3. And in fact, you have developed an idea of, oh, absolute values just make things positive. Well, technically, the definition of an absolute value is how far is -3 away from 0? It's 3 units away. How far is 5 away from 0? It's 5 units away. So the absolute value bars are really asking for distance on the number line, how far something is away from 0. Okay? It's much easier to just teach and explain, oh, it just makes it positive, and it's like, that's easy. And so we tend to learn something by what's easy, but sometimes we lose its meaning. Well, we use the same thing here for the absolute value. So if you were asking and drawing this out, and I went to 6, 3, there's that point. Here's the vector. If I want to know the length of that vector, I'm still asking how far away is it from 0. And in this situation, you can easily draw a right-angled triangle and do a squared plus b squared equals c squared, just like you would have done before, and get the square root of 45. So we would say that the magnitude of OA is equal to the square root of 45, which, if you want to practice your skills with simplifying radicals, that's always good. Textbook might list it as 3 root 5 for your worksheets to get that as an answer. So the magnitude is just a squared plus b squared equals c squared. It's just the same thing with the triangle. Now what makes, and what we're going to find out is fascinating about vectors is we can do math with vectors and they can sort of float all over the place. Some of the mathematics that we're going to be able to do with vectors is very cumbersome with our old techniques of mathematics. And so now if we free up some of our rules from our old techniques and develop new rules with vectors, we can solve a lot of things really easily, especially if we're working in 3 dimensions. So our vectors math that we're going to do here is going to really help us figure out 3-dimensional math, which is nice because most of our life is lived in 3 dimensions. It's not like, oh, I'm going to go live on a paper for a while and just have flat, boring life. Okay. So, first of all, vectors are equal if they have the same magnitude and the same length. In other words, they're parallel because they have the same direction. Sorry, not the same magnitude and same length. Same magnitude and same direction. So it doesn't matter where they are, and often vectors aren't fixed. They're just floating. You can move them wherever you want. And they're equal if they look like this. We call vectors that are multiplied by a scalar, right? You get something that's the same direction or opposite direction if you multiply by -3, but they'll all be parallel, but some of them might be in the opposite direction. A unit vector has a length of 1. And this is going to be very helpful in solving some questions. Here are the standard unit vectors. You have a unit vector I, so if you want, you can put the arrow over top of that. And the unit vector J. Maybe we'll do that. All the bold ones, we'll practice putting the arrows over top because just like plus C, I have to check that on every single question that you never forget the notation on a vector. So we'll have to make sure that we're really practicing that. So the vector I, this one, remember that the 1 at the top, that's your x direction. So this would move 1 unit to the right. And this 1 at the bottom, that's your y direction, that would move 1 unit up. So this is your vector J, and this is your vector I. We can add arrows on top of those. So we can write 6, 3 as 6 in the x direction and 3 in the y direction. We can write it as 6i plus 3j. And so you're going to notice that your vector math has a lot to do with matrices math. So if we think of this as I as 1, 0, and j as 0, 1, in matrices, if you had a number out in front, you could just multiply. So this one would be 6, 0, and this one would be 0, 3. And in matrices, if the matrices were the same size, you could add them together, and you added them together by adding the corresponding spots. Same thing as with vectors, they act the same way. So you can sort of think of this as matrices and vectors at the same time. So what we're going to do for each of these is we are going to write all of these vectors in terms of i's and j's. So for example, here, A starts here, the arrowhead goes here, so it ends there. Can you see that he went 3 to the right, and then 2 up? So we can write A as 3I plus 2j. I'll get you to do B, C, and D. So you're going to use a negative sign if your x is going left. You're going to use a negative sign if you're going down. So that's why some of them are positive, some of them are negative. So it is important to see which direction your vector is going. And we'll move to 3 dimensions. So these are our unit vectors. Add our arrowheads to these. We add the unit vector k to go along the z-axis. Again, if you were drawing the 3-dimensional axis on a 2-dimensional piece of paper, you imagine taking your x and y axes, here's my x-axis and my y-axis, and you put it on an angle as if that is a 3-dimensional picture and that is lying on a table. Can you imagine that in 3 dimensions with this still being a 90-degree there? And then you add a z-axis that goes up and down. So this is how you can draw a 3-dimensional set of axes on your piece of paper, because we don't have 3-dimensional paper yet. Take a 4-dimensional binder to fit it into? I don't know. Be complicated. So there are 3 dimensions, and most of our matrices math will be working in 3 dimensions. Like I said, that's a very realistic way to do things, right? Because if you were doing a 2-dimensional question, that's like, okay, we can make some ants run on the floor. And that's very realistic. That's 2 dimensions. A lot of our travel is in 2 dimensions because we stay on the ground, right? But as soon as you go to airplanes flying, well, they have the option to go up and down, left, right, whichever direction they want. So here's our axes. We've got our x-axis, y, and z. Now, if you want to draw -9, so I move -9, I don't know if that's probably not enough fixed, I'm just estimating. -9 along the x, and 3, I can do that one pretty good, look at that, on the y. And that would be, this point here, in 2 dimensions, would be -9, 3, if that was laying flat on paper. Now, when you add that 3rd dimension of z, I'm going to count going up 1, 2, 3, 4, and whatever this length is going up 4, that's what I have to go up from that point, -9, 3. I go up that exact distance of 4. That ends right there. And so drawing in 3 dimensions, this would be my vector as just a way of drawing. So what this diagram is sort of showing is creating that box, that rectangular box with all 3 dimensions, and then you're joining one corner to the other corner. Now, how long is that? How long is that vector on the blue line? Which initially might seem like, oh, is this going to be more difficult? If you wanted to solve this 2-dimensionally, okay, would you agree that you could do a² plus b² equals c² to find the distance from 0 to -9, 3? And once you found this distance, now this makes a new right-angled triangle. You know that this, whatever distance I find there, this distance is 4, and I could do a² plus b² equals c² again. And it's beautiful math because of this, okay? I'm going to call, I want to show you how nice the math works out, because the formulas, like we've got it listed right here. It's just a squared plus b squared is c squared equals d squared. You just keep adding. It's the same idea of a squared plus b squared, but you just added a c squared inside of it, and you're like, that seems too simple, Mr. JR. I don't think it should work out that nicely. Well, if we do, I'm going to call this my A, this my B, here is B and here is B, and this length my C. If you did regular Pythagorean, this black line, which would be the square root of a squared plus b squared. And then if you wanted to find the blue one would be the square root of this side. I mean, it would be this side squared plus this side squared. Well, what happens when I square the a squared plus b squared in the square root? It just becomes a squared plus b squared plus c squared all in a square root. Which, nice to see where it comes from. It's just doing the Pythagorean theorem twice, but it makes, right, yeah, it's kind of relieving sometimes in math where the next stage is just as simple as the first stage. So in 3 dimensions, if you want to find out how long something is, you just need to do a squared plus b squared plus c squared in the square root. So the magnitude of v, so we can show this notation-wise by putting absolute values with v, I'm going to add the arrowhead there, is just going to be negative 9 squared plus 3 squared plus 4 squared. 81 plus 9 plus 16. Oh, close. Square root of 106. Beautiful. So it's just over 10 as far as that length from one corner to the other corner. Okay? So I'd like you to find the lengths of all these. This first one, okay, is just your regular 2-dimensional one. If you want, you could write this as a column vector. We could write this one as a column vector. I'm going to add arrowheads to these just to practice that. All right, let's check how you did. This is your famous 3, 4, 5 triangle. The second one works out to square root of 75. If you wanted to, you could simplify this. Good practice to practice simplifying. That would be square root of 25 times the square root of 3, so that's 5 root 3. And then in C, if there's nice 3, 4, 5 triangles with Pythagorean triplets, now in 3 dimensions, there are nice 3-dimensional ones. This one's exactly has a length of 7, which is kind of cool that it works out so nicely. And the next one, you would do the same thing. You would set up. You know that its length is 10, so a squared plus b squared equals c squared. Does it bother you sometimes when you have a formula that has a squared plus b squared is c squared and you have to make b a? Does that ever bother you? It's amazing how stressful that can be. But it's like on the IB exam this year, they had a question where they said, write the answer y equals mx plus b, but make your yx and your xy, just to mess things up. I was like, why? It's an exam. People are stressed out. Don't do that. So a unit vector can be in any direction. Our unit vectors I, j, and k have specific directions, but you can have a unit vector in any direction. You put all your unit vectors together in 2 dimensions, you get your unit circle. You put all your unit, I don't know if they have a unit sphere in 3 dimensions, but probably there is. So here's the notation for a unit vector. We put a little hat on it, make it feel happy. Okay? Oh, just practicing. Awesome. So, put our arrowheads over these. We want to find the unit vector in the direction of the unit u. Now, u, I'm just double checking. Isn't this the one that we did in part C? Are these the same numbers, 6, -3, 2? So we're going to save some time here. We already have figured out that its length is 7. So how do we write our unit vector? Okay, and I'm going to show you there's multiple different ways you could write this answer. My favorite, I like using column vectors. So my favorite would be, if this one has a length of 7, does it make sense that I want it to be in the same direction, but with a length of 1, I would just have to chop it into 7 pieces. Well, chopping something into 7 pieces would just be taking the original one and dividing it by 7. And I like to keep that 1/7 out in front. Because if you're doing math, you could, as a second option, put that 7 in and write it that way. But then any math that you're going to be doing with each of those elements or each of those numbers, now you're dealing with fractions first, whereas it might be easier to work with the whole numbers first and just do your fraction at the end. And of course, you could write this I got lazy. I did my only half arrows. Old habits. You could write it that way as well. Okay? So technically, for my mind, that's the cleanest. That looks the nicest to work with. This notation doesn't look clean to me. It's like just, and then if I forget one of those arrowheads over the I, the J, or K just once, then I'm already halfway to losing a mark on a quiz. So that's why I like using the column vector the best. But those are just 3 different ways that you could write the same thing. All right, I'll get you to try these ones. Here are the answers. So first of all, you find the length. The length of u is the square root of 29. So then the unit vector will be 1 over the square root of 29 times what you started. You're just going to divide it into that section. And here the length is square root of 61. You divide it by that, and you get your length of 1. Now, just a little bit of connection to math that you've previously done. Oh yeah, here you can check it. But let's say I take in 2 dimensions my 3, 4, 5 triangle, and I change this into a unit circle question where I say, okay, here's my unit circle. What's that point? Okay? So what did we do with our unit circle? Well, we might have learned in our unit circle that coordinates on our unit circle are cos theta comma sine theta. Cos theta happens to be 3 on 5, so 3/5, and sine theta would be 4/5. And really, that point, 3/5 and 4/5, is just 1/5 of 3 and 4. Because the length of the 3, 4, 5, its length is 5. When I reduce it back to my unit circle, I'm wanting a length of 1. And so it's just kind of neat to see those connections of how, oh, we did this with unit circle, now we could do the same thing with vectors, and it makes a lot of sense. Okay. Oh, I don't want to do that one, show you the answer, I want to do that one. So, find a vector with a magnitude of square root of 7 in the direction of the vector. So we're going to call this vector V is equal to 5, negative 4, negative 3, and 2. If we did a squared plus b squared plus c squared here, 25 plus 9 is 34, plus 2 is 36. Does it work out that nicely? 25 plus 9, 34, plus 4, oh, 38. So our unit vector would be 1 over the square root of 38. And our answer is just to take our unit vector, and we're going to have to multiply it by the square root of 7. And I would leave my answer just like this. And the idea of using a unit is something that you use a lot of, okay? It's in your grocery store. You go to the grocery store. I'm actually disappointed a little bit with the grocery stores because they've taken math away from people. You just have to look on there, and now they tell you the price, and right beside it they tell you, this is the price per 100 grams. They take all the fun out of grocery shopping. Because it used to be like, ooh, should I buy this bag of sugar? Or should I buy this bag of sugar? And you actually had to know some math to figure out which was the better deal. Now you just have to look at the numbers at the bottom, and they tell you which one's the better deal, which I have to admit is kind of nice because I don't want my shopping trips to take super long every single time. But if you're shopping, you're often using a unit vector, or the idea of a unit vector, the idea of one unit, to figure something out. You're looking at, oh, here's a bag of apples that has 10 apples for $5, and I can buy 8 apples for $3. Well, that's probably a better deal. But what do? You would say, well, 10 apples for $5, that means each apple is 50 cents. 8 apples for $3, divide by 8, that means, oh, each apple's under 40 cents. This is the better deal on the price per apple. So you can find out that unit one and use that as a cost comparison. We can use it here because it's hard to go directly from here to here, but if you find the unit vector first, you can find a vector of any length you want by just taking the unit vector. If I wanted this one, same direction, length of 7, multiplied by 7. Length of E, multiplied by E. I don't know why you'd want a vector of length E, but you could have it if you want. adding and subtracting vectors. When you are adding two vectors, here this diagram says I could add vector u plus vector v, and it would be the same as vector w. So you have a starting point, you have an ending point, and in vectors, they're not worried about you going off in wrong directions. Like, if I was wanting to get from A to C, I would probably want to walk there directly to save time. Vectors aren't worried about saving time. They're like, you can get to C, whenever you want to walk in different straight lines, you can go to B first, and then you can get to C. You're still at C, I don't see what the problem is. They're not concerned about what's the fastest way or what's the slowest way. They're just sort of saying, we're going from A to C, and we could say that when we're adding vectors, that AB plus BC will equal AC. And something that's kind of connected to matrices is that if you're adding two vectors and this middle number is the same, they could be combined and just call it A to C. See how that connects together? And so we got to add some arrows here. Oh, fun times. And in definition, we call the vector W the resultant of vectors A, B, and B, C. So we're going to find, where does this come useful? Well, if I'm pulling on a sled in this direction, and Roham's pulling on that direction, and we're both pulling at the same time, the sled is going to move forward. But it's not going to move towards Rohan, it's not going to move directly towards me, it's going to sort of move in between us. We're going to find out that whatever my vector is that I'm pulling, and whatever Roham's vector that he's pulling, we can move mine over here, attach it, and draw a new line, and that will be the vector that the sled is going, and the direction that it's going. Now, if we have the vector A to B, and we have that as u, then going in the opposite direction, we just need to add a negative in front. Those two, they're going in the same direction, just opposite ways. Okay? Then we can show that with a negative. They have the same length, just opposite directions. First, we'll do this the long way, just once. We'll do A plus B on the graph. A is 2I minus J. So if I wanted to draw A, I can start here, 2 in the x direction. There is matrix A. If I want to do matrix B is 1 to the left and 3 up. So I could start here, 1 to the left and 3 up. This is matrix B. Now, if I wanted to take A, I can drag it anywhere, here's A, and add B, this is what's happening. I'm going A, which has this direction. I would end at this point right down here. Then I would add B, which is this direction. And my resultant right here the result is I started here, all I've done is I've moved 1 to the right and 2 up. So the answer to A plus B is 1 to the right, 2 up. I can write that as a column matrix. Okay? It's going to be annoying to draw them every single time. we're going to see if there is some way that I could possibly think of some mathematics. If A is 2 and negative 1, and B, which is the green one, is negative 1 and 3, how could I possibly get the answer just looking at the column matrices? So in the next one, well, if B is negative 1 and 3, and I want to subtract A, and A is 2 and negative 1, are you okay as the resultant here would be, how did I do that without drawing it? So obviously we're dealing with some very complex mathematics at this moment. And what would I do if I had two B's? So I'm going to write 2 times B plus 2 times A. If I wanted to draw that out, I would say, okay, here's one B, here's another B, then I have one A connected to that, and then another A connected to that, and then I need to figure out this. And there's some way we can do it without drawing the pictures, okay? Where I like to pretend it's beyond my teaching ability. If anybody figures it out, that would be wonderful. But I think, judging by your smiles, everybody has figured it out. Just like matrices, you're just adding and subtracting the corresponding spots. If you have a scalar in front, that 2 multiplies both of those, and the 2 multiplies both of those, so you'd have 2 times negative 1, negative 2, plus 2 times 2, 4, you would get 2. And it shows up on your diagram as well. So it's important to know what's actually happening. This is how someone travels. They traveled 2 in the B direction, and then 2 in the A direction. This is where the red is the resultant of where they started and where they ended up. And just like a column matrix, if you were given, I actually find if I'm given matrices in the I, J, and K, I like to just switch them to the column matrices. It makes all of your mathematics really easy. So we'll finish up here. If P and Q, we can add these together. It's really easy to get 1, negative 1, and 7. If you had P minus a half Q, P minus half of that, so it would be plus 1 will be 4. Negative 1, this will still be, oops. This will still be negative 1, and 4 minus, half, minus 1.5. No problem. Sometimes it's nice to write out the equation in vectors first that makes sense. If I go from A to B and then B to C, that's the same as going from A to C. That's where I'm going to end up. So as far as putting things in here, I know that A to B was 4, 7, and negative 3. I know that B to C is negative 1, 2, and negative 5. Therefore, if I add them together, that is A to C.